Let's examine some of the key ideas that we're going to look at in the first part of this packet. The first is learning a change in tandem, and that is when we're going to compare the input and output values between two functions. Finding the average rate of change, identifying increasing and decreasing intervals of function, we've all done this. Identifying concavity, remember concave up looks like this, concave down looks like this. In both cases here, we're increasing, but this is concave up, and hopefully you can see concave down. Inflection points is when it switches from increasing to decreasing, or vice versa. Finding the local or relative and global or absolute maximums and minimums. Remember, if there is a global or an absolute maximum or minimum, it has to consist of one and only one point that stands out as absolutely the highest point or the lowest point on a graph. We're going to find the zeros, their multiplicities, determine the multiples are even, odd, or neither, and then describe the end behavior of a function. At the very back of the front page as you follow along here, we are going to look at this particular example here. I'm going to circle it, you can write along here, and we are asked to identify the domain and range. Now, if you had a graphing calculator, really easy to plug that in and see what does that look like. But without a graphing calculator, how do you do this? Well, the first thing is let's look at the domain. So our domain, we know that the value inside this radical here at the minimum could be 0, could be equal to 0. So if I take this quantity, x plus 7, and I say this quantity has to be greater than or equal to 7, I'm able to solve, right? And so x's have to be greater than or equal to negative 7. Now, this just shows two different ways that we can represent both the domain right here, and we can also see the range in this position. As I go through this, please do me a favor, and if you have any questions, write them along the left-hand side margin. On the very front of your paper, it looks like this, and this is where if we come across any formulas that we do need to touch back on before the test, we're going to write this down, or areas of concern that you may individually have about topics. Okay, rate of change. So again, off to the side, if you have any questions, please write them down. Rate of change is always, for any function that we are going to analyze, is always going to be the change in y's over the change in x's, and this is a formula that you touched on in 8th grade, some of you in 9th grade. Here's an example in which they ask you to find the average rate of change. This is definitely a type of problem you're probably going to see on the test, and they give us an interval. So I think that the most common misconception here, and looking at this without anybody explaining to you, is that students see this and they think of this as a coordinate, like an xy. So no, these are both x coordinates. We want to know what is the average change between x equals -1 on the graph to x equals +3, and we're literally simply going to plug them in. And so I'm going to call this my x1 and this is my x2, and so I'm going to plug this in here to get an output. So you can see I put a 3 in here, and when I plug 3 in, I get 3 squared times 4, 3 times 3 plus 2, and I get an answer of 47. I do the exact same thing, -1, -1 squared, do all the math, and I get an answer of 3. So I subtract these two. It's the change in y's over the change in x's. This is the average change. So between -1 to 3 on this particular graph, it goes up, on average, up 11 over 1. Let's go to the next. This next page is just two things I want you to recognize. Whenever you describe increasing or decreasing intervals, we always describe them in terms of x values. So for instance, the interval that is increasing here, it comes in terms of x's from the far left, and it continues to increase. I'm going to have to estimate there to -2.2. Now at -2.2, if I'm correct there, at -2.2, it's neither increasing or decreasing, it's resting. This would be an area that's decreasing. We call this an inflection point. And so here it's decreasing from -2.2 all the way to an x value of maybe that's +2. There's another inflection point, and now this is increasing. So it's increasing from 2 as it moves to the right, it increases. I want to hit on that. Now down below here, I want to touch on different terminology that means the same thing. So when we say absolute or global maximum or minimum, it stands out as the highest point. So this point would be known as an absolute or global maximum. This is an absolute or global minimum. Now, we still have a high point. This is still a low point. This is still a low point and a high point. These would be known as local or relative max and mins. You can only have one absolute or global maximum. You can only have one absolute global minimum. You can have unlimited number of local maximums and minimums. When you jump into calculus, you're going to learn more about concavity as it relates to derivatives. At this point, I think this is a great picture to show us. In fact, I would go to that front that says Polynomial Functions Toolbox, and I would draw a picture of these, as we saw one question like this on the first practice MCQ that we did. So we can see in these positions, in both cases, we're going up. We're going up, we're increasing from left to right, we're increasing from left to right, but notice this is a concave down, and this is a concave up. Pretty self-explanatory. Same thing here. We're decreasing from left to right as we read it in terms of x values. We're decreasing from left to right in terms of x values as we analyze it from left to right. But this is concave down, and then this is concave up. I would definitely draw these pictures in this exact form on the front of the Polynomial Functions Toolbox. Here are some great examples of inflection points. So it says here, inflection points occur when the rate of change of a function changes from increasing to decreasing. So here we go. This is the obvious one. We're going to go from increasing to decreasing, and the inflection point is right here, or from decreasing to increasing. But now when we think of concavity, so when we think of here, we're still changing here. We're changing here. So let's go back to that graph. We can do that really quickly. And we can see the left side of this portion right here, this portion right here, represents here. So it is decreasing, but it's concave up. It's decreasing, but it's concave up to the left of the inflection point. And if we come back here, let's look at this point. This point right now, whoops, hit the wrong one here. This point looks like this point. So it's decreasing, but it is concave down, concave down. So both of them are decreasing, but it's on the left of the inflection point is going to be decreasing concave up, and then to the right is decreasing concave down. All right, so we can see that. Let's go down here. Intercepts and zeros. You guys are already familiar with that. X-intercepts and zeros. So zeros are going to occur where we have an intersection with the function and the x-axis. We also need to keep in mind we do have the y-intercept. So if it asks just for intercepts, you need to assume you need to both state the x-intercepts and the y-intercepts. For this page, the only two things that I would make sure you can do is one is, can you correctly identify where it's increasing and decreasing, and do it in interval notation, and then given a calculator, can you do the exact same thing? So if it provides you with a graph, are you able to show where it's increasing and decreasing, as well as identify what our maximum and mins are? And so if we look really quickly at this one, if you're given this particular graph, I do want you to be aware, with this polynomial, this arrow insinuates it's never going to stop going up, so there is no global or absolute maximum. Likewise, there is no global or maximum or absolute minimum. We do have a local or relative maximum and minimum, and you can use your graphing calculator. Really quickly, what is a polynomial function? Well, a polynomial function are functions that you've worked with all the way back to middle school, so linear, quadratics, square root. It is not exponent. So polynomial functions are functions in which, when we look at the function, let's just put some other numbers here. Let's make that a -3. When we look at the actual equation of the function, when we look at the exponents can never be negative, and the exponents can never be a variable. And since they can never be a variable, that's why exponential functions that look like this is not a polynomial, because we do have a variable in the exponent position. So polynomial functions, once again, are equations in which when we look at the exponents, they have to be positive real numbers. There is no negative numbers, and there is no variables in this position. The degree is going to be the largest exponent on a variable, and the leading coefficient is going to be the number. Before we go on to our next page, we wanted to show the table of values models a quadratic function. So if something models a linear function, this is all going back to freshman level math. If something models a linear function, the difference, as we look at the output values, we have to make sure that when we do this and we're looking at the x values, they're consistent. So we're consistently here going up by 1. That's first before we analyze the output values. Once we know they're consistent, our x values are consistent, we can look at the y's, and we can look at the change or the difference. So here I'm going down 8, 6, 4, 2, 0, and 2. That's the first difference. If all of these numbers would be exactly the same, then we would say this models a linear. Now we want to show why it models a quadratic. When you analyze the first difference, we can see we're going up by 2, adding 2, adding 2, adding 2. When the second difference is exactly the same, it models a quadratic function, and you can see how they were able to do that down below. Interesting one, and definitely one we want to touch on. If you could look at what we are provided here. So we want to find all the zeros and the corresponding multiplicities of the graph. So you can see the first thing they did is they factored an x, and then from this portion right here, they were able to factor that into x squared minus 1, and x squared minus 1 breaks into x plus 1 and x minus 1. And so they were able to factor that. So we have x minus 1, if you want to write this out, x minus 1, x plus 1, and x plus 1. That's what it looks like right now. So when I actually find the zeros, I set each one of these equal to 0, and I get x equals 0, 1, 1, negative 1, and negative 1. And like one of our MCQ questions, if they asked you to describe the zeros, there would be actually only 3 distinct zeros here, because there's a 0 that occurs, or an x-intercept at 0, at 1, and at negative 1. Now, this relates to multiplicities. How many times you see that 0 repeated tells you the multiplicity. So this has a single multiplicity because there's only one 0 of x equals 0, one answer. This, we can see it's written twice, and so we say that it has a multiplicity of 2 because it's there twice. This also has a multiplicity of 2 because it's there twice. And remember, with multiplicities of 2, it bounces off. It bounces off the x-axis. If it was a multiplicity of 3, let's just add this in for the sake of understanding. If I added an x plus 1 there, so now we have 3, then at this point it would come up and we would say it snakes through. It snakes through. That would look like cubic or multiplicity. Let's look at example number 2. So we're provided with a polynomial function, and we're told that 2, or above that, please write x equals 2. It's a 0, it has a multiplicity of 2. That means if x equals 2 is a 0, then when I write it in factored here form, it's x minus 2. And why did I write it twice? I wrote it twice because there's a multiplicity of 2. Now, if I go ahead and I expand this, it would be front, outside, inside, and last. So x squared plus 4x plus 4. And that's where they have this portion. So without using a graphing calculator, we want to find all the zeros, and then we want to list their multiplicities. So we were told this. Again, x equals 2 is a 0 or an x-intercept. When I write it in factored form, remember we switched the sign. I wrote this down twice because the multiplicity is 2. So I'm going to do long division here. If you learn best by seeing me do it live, I'm going to press. It's been quite some time since you've done this. I don't have much room here, but I'm going to ask myself, 1 times what value gives you 1? We need to make sure that everything inside is represented. So the degree inside is a 4, so we have 4, 3, 2, 1, and this is x to the 0. Everything is represented. If something was missing, we'd put a 0 in that position. For instance, if we had no coefficient here, there was no x to the cube, we'd write 0x cubed. All right, so 1 times 1 is 1. Okay, so I know I need to have a 1. Now, how many more x's do I need to add to x squared to come up with x to the 4th? And it is x squared. So up above here, in the right position, I'm going to write 1x squared. Then I'm going to multiply through to get 1x to the 4th, multiply, minus 4x to the 3rd, multiply, plus 4x squared. Then I'm going to change the signs on everything on the second row. Change, change, and change. And I'm going to add straight down. Negative 13x squared, adding straight down to get 6x to the 3rd. And these two should be additive inverses. Okay, let's bring down the next number. And let's do this again. 1 times what is 6? 1 times 6 is 6. I need 3 x's and I only have 2. It means I need 1 more x. So in this position up here, I'm going to put a positive 6x, and now I'm going to multiply. So 6x times 1x squared is 6x cubed. Positive 6 times negative 4 is a negative 24x, and multiplying again to get a positive 24. Show it a square. Now I'm going to go through and change the signs of everything on the second line or second row, and I'm going to add down. So when these add together, I end up with negative 44x. Let's see, I got to make sure here. This looks like it's supposed to be addition. Yes, it's supposed to be addition. So the difference between 13 and 24, the difference is 11, so it's a positive 11x squared. and these are additive inverses. Let's bring down the next number, a positive 44. Once again, 1 times what is 11? That's 11. I have an x squared. I don't need to add any more x's, so plus 11. I multiply it through, and I get 11x squared. Multiplying through is a negative 44x. Multiplying through is a plus 44. Change the signs and everything. Change, change, and change. And you can see everything adds now to 0. What does this tell us? It tells me if I multiply these two, I end up with this original polynomial. So I already know that these two provide me with the zeros x equals 2 and x equals 2. That's why it's a multiplicity of 2. So I'm going to go off to the side, and I'm like, oh, I can't factor this. I don't know two numbers that multiply to give me 11 and add to give me 6. And so here you can see that then you have to know the quadratic formula. So if you don't, you're going to go to your front side and you're going to write down the quadratic formula. This is something you must know. Must know. When you can't factor something, it doesn't mean you can't solve it. It doesn't mean you can't solve it. And it also doesn't mean that just because you use quadratic formula, you're going to end up with a complex solution or a solution that has an imaginary answer. So I plug in the appropriate numbers for the A, B, and C. And this is what I end up with. After I simplify, this is what I end up with. So here are my answers. I have x equals 3, x equals 3, x equals negative 3 plus the square root of 2i, and x equals negative 3 minus the square root of 2i. So I have one distinct 0 and two complex answers. This is a multiplicity of 2, multiplicity of 1, because it's only written once, multiplicity of 1. Great. Next part is even or odd functions. You definitely want to take this back out. If you've not added this into your front cover, please do so. These are important key things. Please take time to write this down. Press. I'm looking at the answer. Let me zoom in here. I'm going to follow this. Now notice that when I look at even and odd, they both contain this. They both contain this. So let's try this first of all. Let's start by zooming in here. I want to know, is this even? Is it odd? Or does it matter? So let's start with this. I'm going to choose a very simple number. I'm going to stay away from 0 and 1. So I'm going to choose x equals 2. So let's figure out what f of 2 is. So 2 to the 4th, I have 3 times 2 to the 4th minus 8 times 2 squared plus 3. 2 to the 4th is 16. 16 times 3 is 48. 2 squared is 4. 4 times 8 is 32. Now 16 minus 32. 48 minus 32 is 16. 16 plus 3 is 19. So f of 2 equals 19. Now I'm going to try f of negative 2. Okay, so I'm going to be lazy right now. I know that if I take negative 2 and I take it to the 4th, I'm still going to get a 16. Whether it's negative 2, whether it's negative 2 or positive 2, when you raise it to an even exponent, you get the same answer. So this is still going to be negative 2 to the 4th. It's still going to be 48. Same thing here. I have negative 8 times negative 2 squared. And this is still going to be 4. 4 times negative 8 is negative 32. I'm going to end up with the same answer. So f of negative 2 is still going to be 19. Let's go back. When you take a value that you choose what it is, I'd stay away from 0 and 1. When you take the value and then you change the sign on it and they're still the exact same outputs, we can say this is even. Now what if this didn't work? What would I do next? If this didn't work, and then I would take and I put a negative sign in front of f. So I would take this original value and I put a negative sign in front of it to see now does it equal the same as the negative. If it did, it's odd. And if it doesn't, it's neither even or odd. Hopefully they have another example for it. Another example to try. Again, I'm just always going to stay with my 2. So I'm going to do p of 2 for this problem. So 2 to the 5th power, 2 to the 5th is 16 times 2, that's 32. And then I have 6 times 2 to the 3rd. 2 to the 3rd is 8 plus 5 times 2. So I have 64 plus 48 plus 10. Now, when you're adding, hopefully you know this, the order you add things in doesn't really matter. So I'm just going to add 6 or 10 right on to 64 to get 74 plus 48. 12 carry the 1, 11 is 12. So p to the 2nd is 122. All right, now I'm going to switch it up and do p to the negative 2. If I get a 122, I know it's even. Here we go. 2, and now I'm going to take negative 2 to the 5th plus 6 times negative 2 to the 3rd plus 5 times negative 2. Let me press pause and get it clear. Alright, so right away, I know I'm still going to get a 32 from this, but it's going to be negative because I have an odd number of negatives. So 2 times negative 32. Same concept here. I'm still going to get an 8, but there's an odd number of negatives, so this is going to be a negative 8, and this is going to provide me with a negative 10. So I have negative 64 minus 48 minus 10. Okay, well, negative 64 and negative 10 give me a negative 74. And, okay, I have the exact same sign, so I get to add them together and keep the sign of a larger number. Okay, add them together. 12 carry the 1 is 11. Okay, keep the sign of a larger number. Okay, so I have p of negative 2 equals negative 122. All right, so this is what I have, and now I'm going to go back here. So I took 2 f of 2, and I took p of 2 f of 2, whatever. I took p of 2 and p of negative 2, and they were not equal. The outputs are not equal. This is not even. All right, now, this is p of negative 2, right? This is p of negative 2. So I'm going to check, is this odd? So p of negative 2 is equal to negative 122. What does this mean? It says write down, first of all, what is just p of x? Well, p of x is 122. And then it says put a negative sign in front of the value. So I put a negative sign in front of the value, and we can see the outputs are the same. And that's why example number 2 is odd. The next part we're talking about is going to be end behavior of polynomial functions. Now, in class, we represented it like this. We did something like f of x goes to what as x goes to negative infinity, and f of x, or your outputs, go to what as x goes to positive infinity. And so we would look at the graph, and we look at the far left-hand side of the graph, and we would tell, is it going up? Hold on one second. Is it headed down, or is it constant at some value? Same thing here. Go to the very end of the far right, and is it going up? Is it going down? Is it constant at some value? And that's what we would plug in here. If it was going down, we put in negative infinity. If it's going up, positive infinity. And then we put the value, the y value that's constant. So here they're getting a little bit fancier with us. And so how they're writing this down is this says, okay, you ready? So I'm going to come up with an example, and we can see one here. So the first thing you look at, I could see by helping students in that do directed study in periods 1, 2, and 4 that there's definitely some confusion here, or you forgot it. Maybe you previously learned it. So let's start with 3x to the 4th. Let's go negative 5x squared, 7x to the 3rd, 8x to the 5th. So the first thing you ask yourself is you look at the degree of the polynomial, which is the highest numerical value on an exponent. And we're going to say that each one of these is an example of a polynomial. So behind this is some type of an equation. So for the first example, we first ask ourselves, is it even or if it's odd? Okay, it's even. That tells me the end behavior is either going to go both up on the left and right, or it's going to go both down. When it's even, it's going the same direction, both up, like a polynomial, like a parabola, or both down. Then we go to the number in front. We don't ask ourselves, is it even or odd? We just ask, is it positive or negative? If it's positive, they're both up. And this is how this textbook is using this writing. So when it's even and positive, it says as we go to the right, we can see that our function goes up. As we go to the left, we can see that our function also goes up. Okay? As we go to the right, x goes to the right, it goes up, and as we go to the left, it also goes up. All right, let's look at the next one. Here we're looking even or odd. It's even and it's negative. Even negative means they're both down. As I go to the left, it's going down. As I go to the right, it's also going down. Okay? It's odd. So if it's odd, they're going to go in different directions. Different directions, okay? Two different examples here. So odd with positive. When it's positive, regardless if it's even or if it's odd, when it's positive, the right-hand side always goes up. Always goes up with your right hand. So in this example, we have odd, positive, so up on the right, down on the left. So on the left, as you go to the left, you're going down. As you go to the right, you're going up. And that's just reverse of that in this situation. we have odd, negative. So in this situation, we're down on the right and up on the left. As I go to the left, I go up, and as I go to the right, I go down. And here's 4 more examples. Without using a graph and calculator, how can we identify the end behavior of this polynomial function? Once again, polynomial is an equation in which the exponents are real numbers, they are positive, so they're not negative numbers, and also in the exponent position, you can never have a variable. All right, let's get started here. So first, it's already in standard form, wonderful. So we can easily identify that we have, in this case, I have odd, positive. So always ask yourself, what is the exponent, or the degree? Odd, positive. So odd means they're going in different directions, so it's either up on the right and down on the left, or vice versa. But whenever it's a positive, regardless if it's even or odd, it's always up on the right. So how do we write that? As I go to the left, I'm going down. As I go to the left, I'm going down. As I go to the right, I'm going up. Now, if this happens to be an F or a Q where you're able just to provide answers and it's not multiple choice, here's where I want you to recognize in case it's multiple choice. But if you're able to actually just write this in, writing this in like this, and this is P. Okay, writing this in like this and saying, okay, as I go to the left, I'm going down, and as I go to the right, I'm going up. That would definitely suffice. Let's do one more here, and if I cover this up, we don't have a picture to look at. First thing, this polynomial is in standard form. So 4, 3, 2, 1, 0, great. So the first thing you ask yourself is look at the degree. Is it even or odd? It's even, so either both up or both down. I know both are going down because we have a negative leading coefficient. As I go to the left, it goes down. As I go to the right, it goes down. Please make sure you have filled this out with what we've gone over. So even or odd, those are important things we have to know. We need to know the quadratic formula and this concave up, concave down, which I think will be very limited on the test. We saw one question that was easy to answer once you knew about concavity. Again, you're going to go much deeper into that next year in calculus. So within my family right now, if you're watching this, my mother-in-law is in her final hours or days of life, and so we're going to stop right now. This was Friday's assignment, and due to my mother-in-law's health and making arrangements for my family to go out of state and to help arrange a funeral, we're going to leave this part. Don't do anything more with this. We're going to leave this part for when I am gone. So you have finished this lesson. Here's how I'm going to know if you actually watched this. Do me a favor, send me a personal message in Teams, not post on the Teams page. Send me a personal message and let me know to what level 1 through 5 that you understood the stuff after we have reviewed it.